Hey guys, my name is William and I'll be your speaker today. We have a chaotic but surely fun lecture ahead of us on the topic of chaos theory. Well, let's get straight into business. So before we even start anything, what even is the concept of chaos itself? Well, chaotic behaviors are mathematical representations that do not converge to a certain function of time. Chaotic systems continue to exhibit seemingly unpredictable behaviors, and everything is, to an extent, just unpredictable and completely random. However, this isn't always the case. I'll talk about why things are seemingly unpredictable later in the presentation when we cover the chaos paradox. Now, let's start with the butterfly effect. I'm sure all of you guys have heard about this either in movies or stories or other books. The butterfly effect is when a small change in the present has a massive impact or effect on events that happen in the future. For example, and this is where the name comes from, killing a butterfly or just simply stepping on a butterfly could eventually set off a tornado in the future. Another very famous analogy used to describe chaos and chaos theory is Laplace's Demon. Now, don't be scared by the name or be frightened or intimidated by the demon itself. This is just a simple concept developed by Pierre-Simon de Laplace, a French scientist. Hold on. Good, okay. If the demon knows the precise location and momentum of every single atom inside the universe, it can have the capability of understanding the past, present, and future values of everything. So this analogy demonstrates how chaos theory has a very strict dependence on initial conditions. Essentially, if you understand the present, you can understand everything from the past to the future. Isn't that cool? Yeah, it's kind of scary. Now, how do these two analogies, the butterfly effect and Laplace's demon, actually relate to chaos theory? As previously stated, chaotic systems have a very strict dependence on initial conditions that seem to be insignificant or not important. So in a way, the future is already determined by the initial condition itself. Chaos theory is just essentially the science behind Laplace's demon and the butterfly effect. There is no possibility for any change to happen once the initial condition is determined and set. Chaos theory was first discovered and developed by a meteorologist named Ed Lorenz in the late 20th century. So actually not long ago. Chaos theory is actually a very new concept. Lorenz was doing some research on climate change and he wanted to redo a trial, but he accidentally inputted the values from a previous test run. Even though he expected the results to stay the same, the data that was collected actually showed that the values had diverged and were completely different between two runs. This still happened after Lorenz did a couple more tests on the same dataset. Now at that point, everyone, including Lorenz himself, were very shocked. So they were wondering, why did this happen? Well, it turned out that the constant values that were inputted into Lorenz's computer simulation were recorded at 3 decimal places, but the computer program calculated and essentially outputted 6 decimal places for every single calculated value. This caused minimal but drastic differences between the initial conditions of the constants. Eventually, due to chaos theory, the points would diverge after several iterations of the trial run. After his discovery, Lorenz developed his own set of differential equations that modeled the behavior of 3 chaotic constants in a 3-dimensional space. In this case, different constant values represented different initial conditions and would lead to different results and solutions due to chaos theory. Now, let's move on to another key concept that we kind of already covered inside this presentation: sensitive dependence on initial conditions. Alright, so initial conditions, the bang of the buck in chaos theory. Any difference in the initial conditions of a chaotic system, no matter how small or tiny or minimal, will have a drastic change and effect on the final solutions and conditions of the chaotic system. Therefore, this creates the paradox that I was mentioning about chaos theory. Chaotic systems are both deterministic and unpredictable. They are deterministic because they are essentially determined by initial conditions. the future is already set by the present conditions. However, it is still very unpredictable because we won't be able to know how every single function or point changes because of the effects of chaos theory. Everything is essentially random, but also predetermined. Now, let's move on to some examples of chaotic systems in real life. First off, weather forecasts. Come on, man, we're not just gonna ignore the fact that chaos theory was first noticed by a meteorologist himself, right? Throughout the course of human history, it has always been very difficult to predict long-term weather patterns. In fact, after the 8th day of the prediction, it is actually more accurate to use historical averages than a computer-based model prediction. These effects are all caused by chaos theory. Therefore, to ensure prediction accuracy, meteorologists actually use ensemble forecasts to create a set of combined predictions. Another great example of this is the double pendulum system. As seen in this simulation, 3 double pendulums are simultaneously dropped at very similar initial positions. However, at around 3 seconds, the positions of the double pendulums actually diverge. This is because of chaos theory. There will never be 2 equal double pendulum movements. Therefore, the double pendulum is an example of a chaos theory system. Similarly, the motion of the Earth, the Moon, and the Sun, also known as the 3-body motion problem, is an example of chaotic behavior in a controlled system. This is because the Earth and the Moon are active objects in relation to the Sun because they rotate around the Sun, but the Sun is a static object in relation to itself. In this case, just like the double pendulum, 2 active objects are moving, but a static object is held in place. Therefore, like the double pendulum, there is no true pattern or behavior of movement because these 2 systems are both chaotic systems. There is no true pattern, everything is random. Alright guys, now let's sum up what we've learned in this lecture. The butterfly effect and Laplace's demon are both analogies that explain chaos theory. Chaos theory was first noticed by meteorologist Ed Lorenz, who then went on to develop the Lorentz differential equations regarding chaos theory. The chaos paradox is a paradox that states that chaotic systems are both deterministic and unpredictable. Last but not least, examples of chaotic behavior include the double pendulum, the 3-body problem, as well as weather forecasts. Now, just before you leave, stay here for a while. Look at this problem and think to yourself, alright? Using these 2 values, 0.5 and 0.50000000001. That's right, that's 0.5, 8 zeros and 1. Using these 2 values, which have essentially the same initial condition but with a very minimal change, try to find what would happen if you ran them under this function. So I have a recurring function here, xn plus 1 equals xn squared minus 3. Try to run these 2 values under this function and do it for a lot of iterations. I'm talking 300, 400, or even like 1,000 iterations. During this time, you'll find a pattern regarding the iterations and the values of the values. The values of the values, what? Now, after you run your iterations in Excel, see if your results diverge. Remember that we have a very similar initial condition, but there is a minimal change that could cause a drastic effect or impact in the future. I encourage you guys to take on this challenge, and please remember to leave your thoughts and findings below in the comments section. Well, I hope you learned a lot about chaos theory today, and as always, thank you for attending today's lecture, and we hope to see you in future videos.